In this part of section 5.4, we're going to take a closer look at sampling distribution. Right? We looked at sampling distribution in class with our introduction activity where we had a uniform distribution. If I just sketch a uniform distribution here real quick, let's see here, adding a little bit of color to it. We saw one where we had 4 classes, each with an equal number in the population. So here is our uniform population. Then our sampling distribution for this represented more of a symmetric distribution, and that looked like, right, where it was exactly symmetric actually, right? And one of the things that is important about these distributions is our mean of the population was 4, and the mean of our sampling distribution was also 4. And that's pretty important here whenever we take many samples from the same population. The mean of that sampling distribution is pretty close to the mean of the original population. That's a pretty big fact here. And you also found standard deviation with these, and you found that the standard deviation of our sampling distribution over here was less than the standard deviation of the original population. So the standard deviation becomes smaller, meaning our sampling distribution is more centered around that mean, which is the same as the population mean. So today we're going to take a closer look at that fact alone, and that's what's eventually going to allow us to do a lot of things with statistics and answer a lot of questions about it. So I'm going to clear that out now, and looking at the warm-up problem, which sampling distribution would be more spread out? All right, and explain why by writing. All right, so the first option is sample sizes of 10 are used, and the second option is sample sizes of 100 are used. Right now in class we looked at just a sample size of 2. So which one would be a more spread out? Samples of 10 or of 100? So pause the video and answer that question. Alright, now a brief description of the problem. In number 1, if our... Let me see here. So in number 1, samples of size 10 are used. Let's say we get something kind of normal. We would expect that distribution to maybe be something like that with our mean right here. No matter what the population looked like, if we took a lot of samples, it might look something like that. Then in number 2, if samples of size 100 are used, we might expect a distribution to look somewhat like this. Right, and again, here's our mean, and those would be the same means. Right? So if, as in the activity we did, we had a uniform distribution, and we'll just so some uniform distribution where our mean is right here, the means of all of these would be about the same. But taking samples of size 10, maybe there's several data values in each of these classes on the histogram. We could take all 10 values from just this class down here, so that would give us means down here in this area. Whereas over here, if we're taking 100 samples, well, it's more likely that not all 100 are going to come from this class. It's more likely that we'll be spread out even more. So it's even more rare to get sample means with greater sample size far away from the actual mean. So as the sample size increases, the standard deviation decreases. So the first option would be more spread out. Right, so going into the notes for today, here are 2 definitions. You can pause the video and copy these down. a sampling distribution is the probability distribution of a sample statistic that is formed when samples of size n are repeatedly taken from a population. Right? So all we're looking at here is, just like with a normal distribution, we're looking at some population, but the population is the set of all maybe means, or we could even do a set of all standard deviations of sampling from a different population. So a sampling distribution of sample means is just that. It's the distribution of the collection of sample means from a population. Alright, so here are properties of sampling distribution of sample means. Again, you can pause the video to copy these down. But two key facts here. First, the mean of the sample means, and we write that as mu, our symbol for mean, with a little x bar, right, which is our symbol for sample mean. So the mean of the sample means is equal to the population mean. Then the standard deviation of the sample means, we write that as sigma sub x bar. So the standard deviation of the sample means is equal to the population standard deviation divided by the square root of the sample size. So here's where we see, as we increase the sample size, the standard deviation of the sampling distribution will decrease. So the distribution is more tightly surrounded around that mean. So this means if we have some population, and let me just sketch the population as being normal, right, is we take a sample distribution, or sorry, let me first draw in the mean of that population. If we take a sampling distribution, right, that sampling distribution is much less spread out and centered around the mean. And as the sample sizes increase, that distribution becomes even closer, even tighter, centered around the mean. And just one last note, this is a terminology note. Standard error. Standard error, or standard error of the mean, is the standard deviation of the sampling distribution. So this right here is standard error. All right. So we don't say standard deviation of the sampling distribution, we just call it standard error to make it simpler. And this leads into the central limit theorem. This is the big theorem in statistics that allows us to do a lot of the inferences that we do, taking a sample and then making some inferences or drawing conclusions about the sample that we can generalize to the population. So if samples of size n, where n is greater than 30, are drawn from any population with a mean mu and a standard deviation sigma, then the sampling distribution of sample means approximates a normal distribution. Right? So the greater the sample size, the better the approximation. And then number two, if the population itself is normally distributed, then the sampling distribution of sampling means is normally distributed for any sample size n. Right? So we saw in our activity that we didn't really get a nice normal curve with our sticky notes. That's because we were only taking samples of size 3, and our original distribution was uniform. So we did not meet either of these conditions. However, we did start to see it be a little bit symmetric. So if we took larger samples, if we took 30 numbers, we would expect it to be normal, or approximately normal. And the mean of that distribution would equal the population mean, or at least be similar to it, and the standard deviation, or the standard error, we could find by taking the standard deviation divided by the square root of the sample size. Right? So these formulas are the same as on that last slide, where this is our standard error. And this formula in the center is our variance formula, and that's just squaring the standard error. Right. So now that we know the mean of the sampling distribution is equal to the population mean, and the standard deviation of the sampling distribution is less than the standard deviation of the population. How does this help statisticians? Well, if we have some unknown value, as we were talking about in class, this could be the average height of Americans, whether it's male, female, or the whole group, even though the whole group of Americans is not normally distributed. If we take samples, we would be able to approximate that value. So we can create a sampling distribution, right? And that sampling distribution would be approximately normal as long as we meet those conditions in the central limit theorem, and the mean of the sampling distribution would be the same as the population mean. So that's how we can approximate or find values that seemingly impossible to find otherwise, right? It would be very difficult to find the height of every single person in the country. Alright, so let's take a look at our examples here. Population has a mean of 250 and a standard deviation of 35. We want to find the mean and the standard error of a sampling distribution of sample means given the sample size in each problem. So we need to use these values as we go through these problems, right? And for all of these, we know the mean of the sampling distribution, or the mean of the sampling means, is equal to the population mean. So we can write the mean of the sampling distribution is 250. Then we know the standard error equals the standard deviation of the population divided by the square root of the sample size. Right, so this equals 11.07. In part B, again, the mean with samples of size 100 should be 250, the same as the population. And this time our standard error is the standard deviation divided by the square root of the sample size, and that comes out to 3.5. Now finally in part C, again, our mean will be the same as the population, 250, and our standard error is the standard deviation divided by the square root of the sample size, and this time it comes out to 1.57. Right, so we can see our standard deviation is getting smaller as we go along. Our standard error is getting smaller as our sample size is increasing. So our sampling distribution is clustered more around the population mean. Right. Now here are your practice problems using the same population, just new sample sizes. So pause the video and try these last 3 practice problems, and then restart the video to check your answers. Alright, for all 3 of these, again, just like before, the means are going to be 250, right? Because the sampling means are the same as the population means. Right? Now with the standard error, this is the standard deviation divided by the square root of the sample size. The sample of 1,000, this comes out to 1.11. Finding the standard error in part E, we take 35 divided by the square root of 2,000. And this comes out to a standard error of 0.78. And finally, in part F, we are finding the standard error with samples of size 10,000. So we take 35, again, and divided by the square root of 10,000. This gives us a standard error of 0.35. And again, as that sample size increases, the distributions are more tightly clustered around the population mean.